In a first presentation, different aspects of fluorescence measurements were discussed. This second presentation focuses on different aspects of P700 measurements and a little bit on near-infrared measurements. Topics are instruments and signals measured, far-red and visible light, parameters, and physiological aspects and applications. WALZ is market leader for instruments that can measure chlorophyll fluorescence and near-infrared absorption signals, P700 or plastocyanin plus P700 plus photosynthesis, simultaneously. The slide shows the three instruments sold, the modular and fiber versions of the dual PAM100 and the dual class NIR. In this tutorial, we want to give a basic introduction of these absorption measurements and what you can do with them, both as independent measurements and in combination with fluorescence measurements. P700 measurements are not as versatile as fluorescence measurements, but on the other hand, their interpretation is more straightforward. Chlorophyll fluorescence is in essence a photosystem-II probe, whereas P700 measurements probe photosystem-I. What do P700 measurements bring above and beyond fluorescence measurements? First of all, photosystem-I is close to the Kelvin-Benson cycle, and the P700 redox state can be used to detect changes in electron flow towards the Kelvin-Benson cycle. Such limitations are called photosystem-I acceptor site limitations. Photosystem-I measurements also give access to processes like cyclic electron transport around photosystem-I. Simultaneous fluorescence and P700 measurements can very effectively be used to detect and identify lesions in the photosynthetic electron transport chain and to monitor photosynthetic control. Looking at the spectrum on the slide, we can ask the question, why do we measure in the near-infrared and not at 700 nanometers, where the P700 spectrum has its main peak? 700 nanometers has several disadvantages. The measuring light would be strongly actinic, and there would be strong overlap with chlorophyll absorption and fluorescence emission. In practice, this wavelength is only used in combination with laser flashes. The near-infrared region has several advantages. Near-infrared light is essentially non-actinic. It has a slight oxidizing effect. Therefore, strong measuring light intensities can be used. And in the near-infrared, the leaf is relatively translucent. In the literature, scientists have measured at 810, 820 or 830 nanometers. But due to the broad peak in this wavelength range, these wavelengths will yield very comparable results. The measurement will be more sensitive to the choice of the reference wavelength, and there values between 860 and 875 nanometers are found. What is measured at 820 nanometers? The main redox-sensitive absorbers in the leaf around 820 nanometers are P700, plastocyanin, and ferredoxin, three molecules that interact with photosystem-I. In all three cases, the oxidized forms are stronger absorbers than the reduced forms. Changes in the redox states of these molecules in time will change the absorption as a function of time. The dual PAM100 measures the 830-870 nanometers difference signal. The use of this second reference wavelength does two things. At 870 nanometers, the P700 signal has decreased much more than the plastocyanin signal. As a consequence, the plastocyanin contribution to the measured signal is strongly reduced. It also reduces signal drift, that is, up or down signal changes unrelated to redox changes, but for example due to osmotic changes in the sample measured. In the schematic representation of the electron transport chain, the three components that show redox-dependent absorption changes in the near-infrared are indicated. Plastocyanin is the electron donor to P700. P700 itself is the reaction center of photosystem-I, and ferredoxin is the electron acceptor on the acceptor side of photosystem-I. Together they allow a characterization of the electron flow through photosystem-I and the processes that affect this electron flow. Photosynthetic control, cyclic electron transport around photosystem-I, feedback inhibition due to low Kelvin-Benson cycle activity. Instruments for the measurement of near-infrared absorption signals have gone through a long development between the end of the 80s and now, and the results of different types of instruments should be interpreted differently. Single wavelength instruments, for example. Initially, there were only single wavelength instruments. Results were often interpreted as P700 changes, but in reality, these signals were a mix of P700 plus a cyanin, a considerable contribution, and ferredoxin, a small contribution. Then came dual wavelength instruments. The dual PAM100 is an example of such an instrument. By using a reference wavelength, the plasocyanin contribution is strongly reduced, and in essence P700 is measured. In the third generation, deconvolution of the signal was achieved. The dual class NIR can deconvolute, that is split, 4 near-infrared wavelength pairs into plasocyanin, P700, and ferredoxin signal contributions. The single wavelength measurements reflect information on all 3 components, but it is difficult to interpret this information. In the dual wavelength measurements, the information is essentially reduced to P700. And now, with the deconvoluted signals, all kinetic information on these 3 components is available to us. The dual PAM100 and the dual class NIR use a single pin photodiode to measure all signals or channels. This means that the different channels cannot be measured simultaneously. Instead, the channels are measured sequentially as blocks of 50 microseconds. This reduces the time resolution, but it is possible to measure all channels separately if a maximum time resolution is important. The block scheme taken from the dual PAM100 manual shows the measurement principle. At 10 kHz, each channel is measured for 50 microseconds every 100 microseconds, and at 2 kHz, there is each time a measurement block of 100 microseconds, that is 2 times 50 microseconds, and then 400 microseconds without a measurement of either channel. Red and blue and far-red light are important tools for absorption measurements. The next 3 slides are dedicated to these light sources. Red or blue light efficiently excites both photosystem-II and I, indicated by big red and blue lightning rods. Overall, red and blue light illumination lead to a reduction of the electron transport chain. Far-red light excites preferentially photosystem-I, but considerably less efficient than red or blue light. Therefore, a much smaller, dark red lightning rod was added, and photosystem-II excitation is even less efficient, and therefore an even smaller lightning rod. Far-red light is used to oxidize the electron transport chain. What far-red intensity to use? If the purpose of the far-red light is to oxidize the plastic nonpool following illumination with actinic light or saturation pulse to determine the F0 dash value, 1 second illumination with any far-red light intensity will be enough to achieve that goal. If the purpose of the far-red light is to oxidize electron transport chain to obtain the all P700 oxidized state with a subsequent saturation pulse, that is a PM measurement for a dual PAM100 or a near max measurement for a dual class NIR, I prefer a high far-red intensity, for example FR20. When working with algae or cyanobacteria, there may be another reason to use far-red lights, and that is to keep the samples in state 1. For this purpose, it is best to use background light of the lowest FR intensity, FR1. This FR intensity is so low that the excitation of photosystem-II is negligible, and there are no S-state changes of the photosystem-II oxygen-evolving complex. Calibration of the far-red light intensity. No far-red light intensities are given because the excitation efficiency of far-red light is very low. It is, however, possible to determine a visible light equivalence with respect to photosystem-I. The figure gives the far-red induced P700 oxidation at 10 different far-red light intensities, ranging from FR2 to FR20. The initial slopes of these curves are compared to the initial slopes of 3 low red light intensities. As the figure on the right-hand side shows, the slope induced by red setting 3 roughly equates the slope induced by far-red setting 8, and the slope induced by red setting 5 roughly equates the slope induced by far-red setting 18. Red setting 7 excites photosystem-II considerably more efficient than all far-red settings. In the next few slides, parameters related to P700 measurements are discussed. Christoph Kluckhammer and Ulrich Schreiber introduced in 1994 several terms for a kind of saturation pulse analysis for P700 measurements. These are the terms PM, yield 1, yield ND, and yield NA, where the sum of yield 1 plus yield ND plus yield NA as a sum of yields is 1. PM is an amplitude. It is the difference in signal between all P700 oxidized and all P700 reduced. With it, the measurements are scaled, and I use it as a rough measure for the PS1 content of the leaf. Y1 is the quantum yield of photosystem-I, that is determined by the fraction of photosystem-I centers that have a reduced P700, and in which a charge separation is possible. YND is the fraction of photosystem-I centers that is affected by donor site limitation. That is, they are in the P700 plus state and a charge separation is not possible. And YNA is a fraction of photosystem-I centers affected by an acceptor site limitation. These centers are in the P700 state, but no charge separation is possible because there is no electron acceptor available. To understand the PM measurement, it is important to understand how the interaction between photosystem-II and photosystem-I works. For this purpose, the P700 changes induced by saturation pulses are shown on a logarithmic timescale. On a dark to light transition, photosystem-II starts to generate electrons, and photosystem-I starts to pump electrons from its donor site, that is from P700 and plasocyanin, to its acceptor site, that is to ferridoxin and to the iron sulfur clusters. This means P700 becomes more oxidized. But, and this is important, these are two independent processes. There is no interaction. Only after about 20 milliseconds of illumination, electrons generated by photosystem-II start to reduce P700. The take-home message of this is that red or blue light overall lead to a reduction of the electron transport chain. But during the first few milliseconds of illumination, P700 becomes more oxidized. Now the PM measurement itself. For fluorescence measurements, the F0 and Fm are used to scale the measurements. For the interpretation of P700 measurements, the PM measurement gives us this scale. Two observations. With far-red light, it is in practice not possible to oxidize all P700. And secondly, with a strong pulse of light, it is not possible to oxidize all P700. In general, as shown in the previous slide, electrons generated by photosystem-II will reach P700 before full oxidation is achieved. Combining a far-red illumination with a saturation pulse, full oxidation can be achieved. A PM determination consists of a far-red pulse of light with which most P700 is oxidized, followed by a strong pulse of red light, which in a few milliseconds oxidizes the remaining P700. This strong pulse of red light subsequently reduces all P700 again. The PM value is then the signal difference between all P700 oxidized and all P700 reduced. Like F0 and Fm, the PM is determined for dark acclimated samples. Determinations during or following illuminations are referred to as PM-. The P700 redox level can be defined by its position between all oxidized and all reduced. The next parameter is YNA. To explain the determination of this parameter, first the P700 kinetics of the first 5 saturation pulses of a light curve are shown. With the PM pulse, the maximum oxidation is reached, value approximately 3. Then the pulses of the lowest 4 light intensities are shown. At the lowest light intensity, the P700 signal stays quite far away from full oxidation, and in the subsequent pulses, the P700 signal comes gradually closer to full oxidation again. In the second panel, the 5 pulses are superimposed, illustrating this trend, which is indicated as well by the arrow. Finally, in the third panel, the YNA determination for the lowest light intensity is shown. The last parameter discussed is YND, reflecting a donor side limitation. This is especially observed at higher light intensities, where the electron flow from the plastic nonpool to P700 cannot keep up with the pumping of electrons out of photosystem-I. A donor side limitation is therefore reflected by oxidized P700 at the start of the strong pulse. To turn this amplitude into a yield, it has to be divided by the PM. In the last few slides, some aspects and applications of P700 measurements will be illustrated. In the Joule Palm 100 manual, a method is described how to determine the plastic nonpool size using P700 measurements. This will not be discussed here. 4 other topics will be discussed: the correction of F0 for photosystem-I fluorescence, the observation that plasocyanin gets oxidized before P700, a regulatory mechanism called photosynthetic control, and the detection of stromal reductance. Making light curves with the Joule Palm 100, it is possible to obtain the light intensity dependence of the electron transport through photosystem-II and photosystem-I. The electron transport rate through photosystem-II is underestimated because in C3 plants the F0 value contains a 25 to 30% contribution of photosystem-I fluorescence. The Joule Palm 100 allows the user to correct for this. The slide shows that in this case, subtracting 25% photosystem-I fluorescence from F0 strongly reduces the difference in the calculated rate between electron transport through photosystem-II and photosystem-I. This correction has no effect on the parameter QP and QN because these are pure variable fluorescence parameters. It has some effect on the values of the parameter NPQ, but it does not affect the trend. It is also important to be aware of the consequences of the close interaction of plasocyanin and P700 for the kinetics of P700 measurements. The figure shows the light intensity dependence of the plasocyanin redox state for a set of plants ranging from shade plants, green curves, to sun-exposed plants, brown to red curves. Especially in shade plants, full oxidation of plasocyanin is already reached at low light intensities. As long as the pool of plasocyanin is not yet completely oxidized, P700 stays largely in the reduced state. P700 oxidation sets in once plasocyanin is oxidized. In the literature, figures showing the linear relationship between the quantum yields of photosystem-II and I are published now and then. What is the meaning of this relationship? As the light intensity is increased, The quantum yields of photosystem-II and photosystem-I both decrease. The quantum yield of photosystem-II decreases because Qa becomes more reduced. The quantum yield of photosystem-I decreases because P700 becomes more oxidized. These are two opposing effects that we can explain on the basis of photosynthetic control. Increasing the light intensity leads to higher electron transport rates and a more acid lumen. The reoxidation of plastoquinol by the cytochrome B6F complex is lumen pH dependent, and a more acid lumen slows the reaction down. As a consequence, Qa and the plastoquinone pool become more reduced, and plastocyanin and P700 become more oxidized. The protons in the lumen are consumed by the ATP synthesis, and ATP is mainly consumed by the Kelvin-Benton cycle. The lumen pH depends on the balance between proton release and proton consumption. When F0 is corrected for photosystem-I fluorescence and the photosystem-II quantum yield is recalculated, the best linear relationship is obtained. The same linear relationship can be obtained by making a graph of the photochemical quenching parameter Qp as a rough measure for the Qe redox state as a function of the percentage reduced P700. Because Qp is a pure variable fluorescence parameter, no correction for photosystem-I fluorescence is necessary. To get information on differences in photosynthetic control between samples, data obtained at one medium light intensity have to be compared. For the plants ranging from shade to sun exposed studied here, a range of values is obtained. The points in the right-hand top corner of the graph reflect sun-exposed plants. These plants have small photosystem-II antennae and a high Kelvin-Benton cycle activity. This means that relatively high light intensities are needed to acidify the lumen and inhibit electron transfer. The points in the left-hand bottom corner of the graph reflect shade plants. These plants have large photosystem-II antennae and low Kelvin-Benton cycle activities. This means that acidification of the lumen occurs already at relatively low light intensities. Therefore, at a chosen light intensity, already a strongly reduced Qa and plastoquinone pool in combination with strongly oxidized P700 are observed. A last slide shows how reduction of the plastoquinone pool by stromal reductants can be made visible. The experiment consists of a strong far-red illumination of a stork's bill leaf, on top of which twice a saturation pulse is applied. During the first period, far-red light initially oxidizes P700, but this oxidation phase is interrupted by transient reduction phase, which is indicated as A. This reduction phase is due to stromal reductants reducing the plastoquinone pool. Then a saturation pulse reduces the electron transport chain again. During the second far-red oxidation phase, the transient re-reduction phase is no longer observed, which is indicated as B. The pool of stromal reductants has been temporarily exhausted. And with this, I finish this tutorial. Thank you for your attention.